Welcome once again to my study. Today we're going to do a supplemental video about a certain problem that turns out to have immense practical significance for all of us. This involves, well, it has many faces. There's the p-hacking, researcher misbehavior, there's the replication crisis in the social sciences in particular. We're going to learn a little bit about each of these and why they happen. One of the benefits of a sort of baby introduction to statistical matters and methods is to be able to see how this sort of thing affects the information you get in online sources and paper sources and that sort of thing, and the degree of skepticism that's warranted. Now, one can become so cynical that you don't ever trust anybody about anything ever. And that's a rather self-stultifying standpoint to end up in. This standpoint, by the way, traces to ancient views in skepticism. There's actually communities of Pyrrhonian skeptics. Pyrrhonian skeptics organized themselves around the effort not to ever believe or trust anything. No evidence of the senses. You could grant that your senses were reporting something. They called that acquiescing to the appearances. But you shouldn't ever conclude anything based on the information that you receive. Once you think about that for a few moments, you can see, most of you will be able to see immediately, that there's an intellectual problem for this view, and it's the problem of paralysis. That was the standard criticism of Pyrrhonian skepticism in ancient Greek philosophy, and it's a serious problem. If you don't ever have any beliefs, if you don't ever draw any conclusions based on the information of the senses, how do you ever decide how to act? Of course, the Pyrrhonians thought they had some sort of response to this problem, but the problem is this: what guides our behavior is what we take to be true or our level of confidence regarding what's true. The idea that you can avoid belief forever is a kind of psychological disease. In fact, William James, the father of modern psychology and one of the initial American pragmatists, said something along these lines. Said, here's the skeptic's problem. Better to go without belief forever than risk being duped. And he said that was a kind of psychological ailment in a person. If you're so afraid of being duped, you also will never get to the truth about anything. So there's some degree of skepticism that's warranted, but total skepticism, total cynicism is probably not advisable. So what we're going to do is look at p-hacking, learn something about it. We're going to talk a little bit about the replication crisis and the more generic problem of when you use the 0.05 level for statistical significance, it's natural to think that you should expect that 95% of the reports you see on studies that were done will be accurate. But it turns out that vastly underestimates the likelihood that any given piece of reporting, any piece that's published, will actually be correct. It will be on to something. Exactly what the rate is hard to say. We don't have any ways of precisely measuring that. But what we can do is show something about how high the error rate, how likely it is that researchers might be wrong when they do a study and it meets the 0.05 statistical significance level. Exactly what the solution is here is not clear, but if you look at work in theoretical physics, for example, on the Higgs boson particle detection experiments that were done in Europe, and look at what their significance level is, it's astonishing how much more stringent the statistical significance level is in theoretical physics than it is in the social sciences. That's worth looking at and contemplating. Maybe the solution is just adopt the standards of theoretical physics, but then the publication business in the social sciences will dry up fairly quickly. So we're going to look at a couple clips from some YouTube videos first on p-hacking and then on the more general replication crisis and the problem of getting things wrong, understood generically when you do these sorts of studies. Let's turn first to a rather low-techy kind of video.
Welcome to What Is This Thing, where I'm going to attempt to simply explain how something works. Today we're going to be talking about p-hacking or data dredging. It also goes by a few. Welcome to What Is This Thing, where I'm going to attempt to simply explain how something works. Today we're going to be talking about p-hacking or data dredging. It also goes by a few other names. P-hacking or data dredging is the process by which you increase the number of hypotheses tested, which increases the likelihood of a positive result. So, for example, in research, in a lot of nutritional studies, it's common to look at a wide variety of things that a person consumes and a wide variety of effects that can be caused by those things that that person consumes. So you might look at whether the person consumes sugar soda or diet soda, or if they consume more fat than normal, or if they consume more cholesterol than normal, or salt, or sugar, or anything like that, looking at all of those variables, while at the same time looking at potential effects of these variables. So weight gain, chances of different kinds of cancers, chances of different kinds of diseases. If you're looking at all of these different effects and all of these different potential causes, you're bound to find one or a few that show a correlation.
In an ordinary study, you have a hypothesis and you run an experiment to test that hypothesis. So think of correlational experiments or data collection. You're looking for a correlation between, you've got some toggle switch, maybe it's high blood pressure, or the lack of it. So that's what you're looking for. And so your hypothesis is something about, say, a high-fat diet. So you look at people you divide your population or your sample, both the population and the sample, into two groups, those that have high-fat diets and those that don't have high-fat diets. So you've got two variables and two values for each, and then you try to see if you get a correlation between high-fat diets and high blood pressure. And your standard is the 0.05 level, standard for statistical significance. That's all very cool. But now suppose you have a very favorite product that you're trying to think about. And so you want to know, does my product in controlled studies or in data collection have any positive benefits for people's health? So then you do all sorts of things with your product. You test for lower blood pressure, better cardiovascular health in some other way, brain function. Can you process information more quickly if you use this product? And you keep going down. So now you've got all sorts of ways to find some positive correlation between the use of your product and some health benefit. All right, now if you apply the same significance level, the answer is that one study out of 20 ought to give you a false positive. One time out of 20, you will detect a relationship between the two variables in question when there really isn't one. So if you're doing multiple studies like that, you're likely to produce some positive correlation. And if you do enough of them, you'll be likely to find some health benefit, which could then be reported. The report, to be honest, needs to explain how many variables were being tested. So, I mean, they could be done simultaneously, but maybe what you've been doing is you have a product, so you've been funding a research center, and they've been working on different studies for the last 10 years, and they finally came up with one. So one of them that we looked at earlier was there were 800 things being tested. This was the one, I think, about chocolate and weight loss. So they ran 800 different kinds of information gathering, and then they published chocolate and weight loss. But notice, if you do 800 studies, whether all at the same time or sequentially, about the relationship between chocolate consumption and various health items, when you look at the 0.05 level, you should expect 40 pieces of bullshit. Let's just put it that way. 40 cases where you found something meeting this standard, and yet there really wasn't anything in the population at large. So that's the p-hacking thing.
This is taken advantage of a lot, and it ends up being picked up by the media. So you'll have a lot of journalists that have articles titled, coffee linked to cancer, coffee linked to anti-aging, sugar sodas linked to heart disease, anything like this. Some of these studies are genuine, but a lot of the reason why you can find this contradicting evidence is because of this p-hacking or data dredging.
So the warning here is that you have to be really careful when you read about these studies to see if they give any indication of exactly what was being done and how it was being done. I'm afraid that some of the reporting is the result of journalists not being well trained enough. If you think about it, think about two kinds of majors that you can have in your university studies. So there are people in education colleges all across the world. There are people in journalism schools all across the world. In fact, Missouri is the home of at least what used to be, I'm not sure, I haven't checked lately, the best rated journalism school in the world. Part of the reason for that is it was the first journalism school in the world. So University of Missouri in Columbia has a great journalism school. The problem with both education and journalism is that they are methods-based courses of study. They are not themselves a discipline. They are not a subject in which you learn something about what the world is like. What you learn about is methods for conveying what the basic disciplines produce. So if you're a teacher, if you study education, you learn about methods about how to get students to learn physics or calculus or chemistry or whatever. But you yourself are not spending time studying those particular disciplines. You're learning how to communicate information. Same thing with journalists. Journalists learn how to write really well, but they might have nothing to say, or they might not have anything going on upstairs. In fact, there's a really famous critic, H.L. Mencken. I'm not sure how you spell his name. Maybe that's right. Maybe it's not. Who said this? This is fascinating. I'm going to write it out and then let you read it. No ideas and the words to express them. That's a journalist. That's the danger of methods-based courses of study. A better plan would be, of course, to learn something and then figure out how to do presentations so that people will actually read what you have learned about. So the danger of journalism is with journalists who don't actually master the information and the methods of the disciplines that they're reporting on. That's not surprising because it's very hard to become the kind of writer. I mean, how many times do you have specific word limits or targets for papers? They're a little bit fudgy. I mean, if I gave you a 3,000 word paper assignment and you turned in something at 2,600, I'd be fine with that. But the margins of error on word counts are much more precise when it comes to space, say, especially in print form. Now that things are online, I think it's much more relaxed because the space pressures get alleviated quite a bit. But the other thing is sometimes you're in a hurry, you have to write fast, and you have an editor who says, yeah, you got to cut this by 700 words. And that's 50% or more of the article that you just read. And that's a really painful thing to have to go through. So journalists are under pressures that make it understandable why sometimes they don't know or don't convey the information we need to process what they're saying. So if you read something about red wine is linked to lower blood pressure, some skepticism about the report should arise immediately, because what you need to know is what's the source of the funding, how was the study done, what exactly was going on. And you should suspect that the wine industry is behind the study and that they're engaging in a kind of p-hacking because they're looking for health benefits all over the place. And look at this, we found something here. As soon as you get any whiff that that's going on, that's a reason to be suspicious of the study. That is what p-hacking involves. All right, let's turn to a bit more of a fancy presentation, and you'll see immediately why I describe it as that.
In 2011, an article was published in the reputable Journal of Personality and Social Psychology. It was called Feeling the Future: Experimental Evidence for Anomalous Retroactive Influences on Cognition and Affect. Or in other words, proof that people can see into the future. The paper reported on 9 experiments. In one, participants were shown 2 curtains on a computer screen and asked to predict which one had an image behind it. The other just covered a blank wall. Once the participant made their selection, the computer randomly positioned an image behind one of the curtains. Then the selected curtain was pulled back to show either the image or the blank wall. The images were randomly selected from one of 3 categories: neutral, negative, or erotic. If participants selected the curtain covering the image, this was considered a hit. Now, with there being 2 curtains and the images positioned randomly behind one of them, you would expect the hit rate to be about 50%. And that is exactly what the researchers found, at least for negative and neutral images. However, for erotic images, the hit rate was 53%. Does that mean that we can see into the future? Is that slight deviation significant? Well, to assess significance, scientists usually turn to p-values. This statistic tells you how likely a result, at least this extreme, is if the null hypothesis is true. In this case, the null hypothesis would just be that people couldn't actually see into the future, and the 53% result was due to lucky guesses. For this study, the p-value was 0.01, meaning there was just a 1% chance of getting a hit rate of 53% or higher from simple luck. P-values less than 0.05 are generally considered significant and worthy of publication. But you might want to use a higher bar before you accept that humans can accurately perceive the future and, say, invite the study's author on your news program. But hey, it's your choice. After all, the 0.05 threshold was arbitrarily selected by Ronald Fisher in a book he published in 1925. This raises the question, how much of the published research literature is actually false?
Okay, that was a nice intro, a really interesting study. And notice what you've got in that case. You've got a hypothesis about whether human beings have the capacity to see the future, or at least to predict in a way that exceeds chance outcomes at being correct. And then you had 3 kinds of images involved. And in 2 out of the 3, you got nothing. And in the 3rd, you got something. Well, this turns out to be publishable material in a highly reputable psych journal, social psychology journal. So that's what is under discussion in this video. But he then turns from that. Let's skip ahead. You're welcome to go back and watch the rest of that video on YouTube. You can search for it if you'd like. It's pretty easy to find. But let's jump ahead to where he gives an explanation of how easy it is, even if there isn't an intention to p-hack. Maybe p-hacking is always intentional, but how easy it is for research to be wrong, even when you're not engaging in the disreputable practice of p-hacking.
The intuitive answer seems to be 5%. I mean, if everyone's using p. But that, unfortunately, grossly underestimates the problem. And here's why. Imagine you're a researcher in a field where there are 1,000 hypotheses currently being investigated. Let's assume that 10% of them reflect true relationships and the rest are false. But no one, of course, knows which are which. That's the whole point of doing the research. Now, assuming the experiments are pretty well designed, they should correctly identify around, say, 80 of the 100 true relationships. This is known as a statistical power of 80%. So 20 results are false negatives. Perhaps the sample size was too small or the measurements were not sensitive enough. Now consider that from those 900 false hypotheses, using a p-value of 0.05, 45 false hypotheses will be incorrectly considered true. As for the rest, they will be correctly identified as false, but most journals rarely publish null results. They make up just 10 to 30% of papers, depending on the field. Which means that the papers that eventually get published will include 80 true positive results, 45 false positive results, and maybe 20 true negative results. Nearly a third of published results will be wrong, even with the system working normally. Things get even worse if studies are underpowered, and analysis shows they typically are, if there is a higher ratio of false to true hypotheses being tested, or if the researchers are biased. All of this was pointed out in a 2005 paper entitled Why Most Published Research is False. So recently, researchers in a number of fields have attempted to quantify the problem by replicating some prominent past results. The Reproducibility Project repeated 100 psychology studies, but found only 36% had a statistically significant result the second time around. And the strength of measured relationships were on average half those of the original studies. An attempted verification of 53 studies considered landmarks in the basic science of cancer only managed to reproduce 6, even working closely with the original study's authors. These results are even worse than I just calculated. The reason for this is nicely illustrated by a 2015 study showing that eating a bar of chocolate every day can help you lose weight faster. In this case, the participants were randomly allocated to one of 3 treatment groups. One went on a low-carb diet, another went on a semi-low-carb diet, plus a 1.5-ounce bar of chocolate per day. And the third group was the control, instructed to maintain their regular eating habits. At the end of 3 weeks, the control group had neither lost nor gained weight, but both low-carb groups had lost an average of 5 pounds per person. The group that ate chocolate, however, lost weight 10% faster than the non-chocolate eaters. The finding was statistically significant with a p-value less than 0.05. As you might expect, this news spread like wildfire to the front page of Bild, the most widely circulated daily newspaper in Europe, then to the Daily Star, the Irish Examiner, the Huffington Post, and even Shape magazine. Unfortunately, the whole thing had been faked. Kind of. I mean, researchers did perform the experiment exactly as they described, but they intentionally designed it to increase the likelihood of false positives. The sample size was incredibly small, just 5 people per treatment group, and for each person, 18 different measurements were tracked, including weight, cholesterol, sodium, blood protein levels, sleep quality, well-being, and so on. So if weight loss didn't show a significant difference, there were plenty of other factors that might have.
Okay, that gives you an idea of the 2 different kinds of problems. Notice the chocolate example drifts over into p-hacking. And p-hacking is intentionally deceptive because you have so many variables. I think he said 18 for the chocolate study. And 18 is a pretty high number. I mean, once you get to 20, if your p-value is 0.05, you have a reasonable expectation that at least one of them is going to show a positive correlation when there really isn't anything there to be found. That's called when there's not anything there to be found. That's the null hypothesis when they talk about that. So we have the discussion morphing over to p-hacking, which we already know is bad. But what's more interesting is the more generic notion of the chances of research being wrong. And his little diagram of all the possible studies that are being done, I think he had 1,000. I didn't actually count. You probably didn't either. It doesn't matter how many little circles he had on his diagram. But the point is, you've got a whole bunch of things being done, and then you have both the percentage of cases where there is a positive correlation and the much greater, or at least possibly greater, things where there isn't anything. So you divide your chart into cases where the null hypothesis is true and the null hypothesis isn't. And we don't know which is which. That's why we're doing the research. So notice the first thing he talked about was the statistical power of the studies that are being used. And that has to do with their capacity to rule out false negatives. The p-value level of statistical significance is aimed at false positives. It's describing how many of the cases that you do testing on will result in a positive result even when the null hypothesis is true. So the statistical significance level is about false positives. Remember when we applied Bayes' theorem, we needed to know the false positive rate and the false negative rate. And that turns out to be the case because the chance of being wrong is a function both of false positives and false negatives. And that's the fundamental story as to why the 0.05 level by itself doesn't tell you about the chances of being wrong. So go back to our chart. Just the little diagram of all the possible studies being done. So we imagine a certain percentage of these cases being ones where there is a relationship, and we're hoping to design an experiment that does that. And maybe we have underpowered, maybe we have well-powered studies. So I have 9 diagrams, 9 little circles in this region. And if we had a study with a statistical power of 2/3, then it will detect the relationship 2/3 of the time. The other third of the time, it will generate a false negative. It will say there is no relationship here when in fact there is. So we need to know something about the statistical power of the study if we're going to be convinced by it, as well as knowing what the p-value is. That's one problem. The other problem is just what is the percentage relationship between cases where there actually is a relationship and the cases where there is not a relationship. We have no idea what the variance is between these two set sizes. But the degree of error that you're going to find, you're going to have both. You're going to have studies being done over here, and you want to know what percentage of those cases are going to be false positives. That's the home of false positives. The worry about false negatives arises from cases where there is a relationship and you just want to know, did I design a good experiment to detect it? Over here, you don't know what the percentage is. But what you do know is that out of all the testing that you're doing here, since there isn't any relationship, you're going to find one 1/20th of the time if 0.05 is your statistical significance threshold. So how many false positives are you going to generate? We don't know that because the percentage of cases where the null hypothesis is true is unknown to us. The best we could hope for is that there really aren't that many things being investigated where the null hypothesis is true. So we're not going to generate a whole bunch of false positives over here. But over here, if we have a statistical power measure on false negatives, we can calculate what percentage of these studies are going to generate false negatives. We can generate an answer as to what percentage where the null hypothesis is true are going to generate false positives. But what we don't know, we don't really in general have any idea what the ratio in the size of the set where the null hypothesis is false and the set where the null hypothesis is true. This ratio number we know very little about. And as that ratio changes, the chances of being wrong go up. So if the null hypothesis is true in the vast majority of research being done, we're going to get all sorts of errors in what gets published. In the example he gave, we had 30 to 40% being wrong. And in that original article that he cited from 2005, that's what the researcher, the statistician from London, was trying to convince people of, that the chances of being wrong are so incredibly high. He called it the chance of looking like a fool when you publish research. Well, maybe looking foolish is a bit exaggerated in the description of the problem, but still, if there's a 30 to 40% chance that you're reporting something when you're just wrong, that high a chance of being wrong is incredibly too high. Nobody forms beliefs and acts on them at that rate of error. It's just too risky to do. Now, exactly how high you want things to go, I don't know. Maybe the 0.05 level, maybe you want your chance of being wrong to be at least as minimal as the 0.05 level. So the statistical significance measure might be a reasonable number to use. But that number is not the chances of being wrong. So if you want your chance of being wrong to be 1 in 20, maybe that's too high, but whatever you think. I mean, people's attitudes toward taking risks varies, and the variance can be rational. So some of you will be much less risky taking when it comes to forming and acting on beliefs, and others will be more circumspect. I mean, there are outliers that are just irrational. Maybe Pyrrhonian skeptics are a good example of being too conservative with respect to forming beliefs and acting on them. But in any case, it doesn't matter where you draw the lines around there. You get some sort of range of probabilities that are reasonable in terms of how much of a risk taker you are and how risk averse you are. But 30 to 40% doesn't sound like something most of us are going to be able to live with. If you've got a 40% chance of being wrong, I think you need to hold off a while and do some more research to figure out what the truth is. In any case, that's a brief little detour into the problem of p-hacking and research that is highly likely to be wrong, or at least too likely to be wrong for us to live with, too risky in terms of research. It's a problem that plagues social science research all over the place. Some proposals are that the level of statistical significance needs to be tightened significantly. Another proposal is we just need to do a lot more replication studies. The problem is nobody gets famous by doing replication studies, and funding isn't typically available for doing that sort of thing. So that's practically not a very good option. In any case, the problem is there, and some of it there's nothing we can do about as cognizers to figure out what to think about, except to realize when somebody says there's something significant here, some healthy skepticism about that is worth taking into account before changing your lifestyle and everything. I'm a person who changes my lifestyle quite regularly based on reports of this sort, but you have to assess, what happens if you're wrong? So suppose you start eating more chocolate. I'd be hesitant to do that because that looks to me like a case where the chance of this research being wrong is worth taking into account because I really don't want to end up obese. So I don't like weight gain. And so when somebody says eating chocolate will help you lose weight, I'm skeptical about that. That's because there's a downside to being wrong involving weight gain. Same thing about drinking red wine. Maybe there's a downside to wine that needs to be taken into account as well. I know my grandmother would like me to think that way, and the fact is I don't. So wine is good. Having a drink with friends is one of the joys of life after you're 21 years old. I have to say that because I expect most of you are not yet 21 years old. Actually, it's not illegal to drink when you're under 21. You have to be doing it at home. I think there are certain restrictions on it. And I'd worry about parents who are getting you to drink a bottle of wine every night. That would probably not be a good idea. But in any case, you got to assess the possible downside risks of following the advice, as well as noting the correlation that's been observed in the samples that were used. What would be nice is if you could check out the background studies to see exactly what they were doing and first verify that no p-hacking was being done. How many independent variables were they looking at? Was it just this one? Also, in the source of the funding, sometimes it says this study involves only one variable, but the funding source has been funding sequential studies involving the same sorts of things. So it's really the same as if you're doing simultaneous investigation of 5 or 10 or 15 or 20 variables all at the same time. This is all worth taking into account and thinking about, and it can be paralyzing. But that's the bad news about trying to figure out what the truth is. It's not an easy task in many areas, and the reason we do statistical studies is because the information we want is not directly observable. It can only be measured indirectly. That's always a risky intellectual endeavor. And I wish you good luck in figuring out how risk averse to be and how risk tolerant to be in the process. But the point of this lecture is just to introduce and make sure everybody has a mastery of the kinds of things that affect the quality of the research being done and the degree of skepticism that is warranted by the practices that are followed when this sort of social science research is being done. In the next video, we'll return to the Geary book talking about causal studies. If you noticed in the video that we just listened to, the chocolate study involved 3 groups. People on a was it a low-fat diet? I think it was low-fat. And then that was one group, people on a low-fat diet who then had chocolate, and also what was called a control group. The reference to a control group is the central feature we're going to learn about when it comes to doing causal studies. If you don't have a control group, there's no hope that your study will give you evidence of a causal link. So let's look at that, and what we'll see again is that newspaper reporting is often sloppy on this sort of thing. The language that I hope you noticed here was the term linked to. Reporters often overuse this word. They use the word X is linked to Y. There's a link between X and Y. And this language is so vague and ambiguous, we don't know what it means. It actually communicates to people who don't know about statistical methods for engaging in causal studies. It suggests that there is a causal link. Because if you say X is linked to Y, people without suitable background think you are telling them that it's a cause. The first is a cause of the second. And correlational studies don't do that. So we'll start looking at that. What's the difference between the two? What are you supposed to find when you're looking for the difference between a causal study and a merely statistical study?